Okay, so here's the first problem. You said it was number 9 here.
Yeah.
Is it possible to fit 3 congruent pentagons, all equilateral and equiangular, around a single point without overlapping? For which pairs of integers is it possible to fit A congruent shapes, each equilateral and equiangular with B sides, around a point without overlapping? This is the crux of Euclid's argument that there are 5 Platonic solids. Okay, very interesting problem. I'm just going to move your thing to the middle here and try to zoom in on it so that we can see. Okay. I think it's in focus, although I always get that wrong.
Alright, so
go ahead.
The first part of their question they answered on their page.
Oh, by
They have-
the picture you mean?
Yeah.
Okay.
You've got 3 congruent pentagons around a single point without overlapping.
Okay. Interesting.
So then I answered the second part. So I was dividing it up in cases by shape.
Uh-huh.
So I divided also up by angles. So if the interior angle is less than 60, you're here, and there's 6 of them.
Okay. So what does 4-3 mean?
So it means that you're fitting four 3-gons.
You could fit 4 equilateral triangles together. Okay. And you can fit up to 6 equilateral triangles. Okay.
So then you have to go to the interior angle being 90, and there's only 4 of them. So you fit 1, 2, 3, or 4 squares.
All right.
Then I go to pentagons, so the interior angle is greater than 90 but less than 120.
Okay.
So you can fit 3 of those. So 1, 2, or 3 pentagons, and then 1, 2, or 3 hexagons.
All right.
Also, the hexagon's interior angle is double the triangle's interior angle, so you can kind of see that.
All right. Nice.
Then the last case is greater than 120, and there's 2. There's 1 or 2 for the shapes that are interior angles greater than 120.
Ah. All right.
And so around a point is 360 degrees, and since you'll never get a shape that has, or in this way, an equiangular equilateral polygon that has interior angle greater than 180, you're just going to keep going up forever.
Okay.
You always have 2 in whatever category you pick over here.
All right. Very nice. And it's actually interesting what they commented on here, that this is the crux of sorry, who did they say it was?
The crux of Euclid's argument that there are 5 Platonic solids.
Okay, so in here, can you tell me what the Platonic solids are?
So there's
there's the tetrahedron,
Which one is that? How many triangles?
which would be 4.
Okay,
That's this one.
alright,
There's the octahedron,
alright.
which would be 8 triangles, which is in here. There's a cube.
Well, hold on 1 second before we jump too far ahead. Now, remember what you're saying here is you can fit 4 triangles around a point.
So I guess that actually would be the octahedron. That would be half of an octahedron.
Okay. So this 4-3 is actually the octahedron. So what's the tetrahedron? How many triangles around a point, each point for the tetrahedron?
The 3.
3-3. Okay.
3.
Alright.
And then for the cube, you're fitting 3 squares around a point.
Okay.
That's this. The dodecahedron, you're fitting, I think it's three pentagons.
Okay.
And then the icosahedron is 5 triangles.
Okay. So I have a challenge question for you on this. Why doesn't 4 squares around a point form a Platonic solid?
Well, 4 squares, that would be 360 degrees, but then you can't fold it up in any way.
Very good. Very good. So those are the Platonic solids.
And that also shows you why there's none behind here, because you only get 2 around a point maximum.
Okay, cool. All right, let's go on to the next problem.